Okay, now let's see if something is working here. Aha. Okay. Good. So we are in business with this one here. And we are in business with this one here as well. So wonderful. Most wonderful good afternoon, ladies and gentlemen. I think I am here on YouTube and Facebook. And what I want to do is a quick live session about how we can analyze basic analysis of data. So data analysis. And I know that a number of students actually do find that quite challenging. So let's see if there is something going on. YouTube is not doing something here. So let's. Okay, YouTube is coming as well. Okay, so data analysis. Now, I would like to know if people can actually watch that and can see it. So it would be nice if you could give me a quick comment with thumbs up and whether you can see it, whether you can hear it. So please, 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 all those of you who are watching this live stream, show me that something is going on and that you are receiving this live stream, please. So any comments would be absolutely fantastic. Right, so okay, we've got comment section here. Right, now what is this about? Lots of students find it rather challenging to determine what kind of equations they want to use when they analyze data. So in general, if we want to just summarize data, we would use descriptive statistics. And in descriptive statistics, we would usually use our data as a total population. However, if we are trying to make inference about other data, so we make predictions, I can't spell properly. If we make predictions about something else, we would use our data as a sample. And that is a general, a rather wide rule. So still, I wonder whether anyone can see me. Can anyone see me? It should be on Facebook and on YouTube. Oh, data analysis, only one person is watching. Aha, okay, good. Facebook, anyone there? Anyone watching? Anyway, so let's say we have a basic data set of the things that we've recorded. So we have, for example, 10, 20, 30, and this is our data set. Now we would like to analyze these data. And summarize the data. So to summarize the data. And what we then will do is we use this data and treat it as a population. However, if we want to use this data to make predictions, about, for example, what would happen if we not just have these 3 measurements, but if we did 20, 50, 100, 500, 10,000 of measurements, if we want to make these predictions, then we would use these data as a sample. Now, let me just quickly run through it, what we can do with these data. I write them down again, 10, 20, 30, and in the first place we want to summarize them. So we want to calculate the mean, and because we are talking about a population, we talk about the mean of the population, and that is usually indicated with this mu. And that indicates the population mean or average. And that's very easy. We just add them all together, 10 plus 20 plus 30, and divide by the number of observations. So we have 3. So that gives us 10 plus 20 is 30, plus 30 is 60, 60 divided by 3. So the population mean in this case would be 20. Now we can also ask, what is happening if we look at the spread of the data? So our data are fairly spread out. They go from 10 to 30. That's actually the range. And we can ask, what is the population spread? Population diversity or dispersion. And in this case, we can use what is called the population variance. And that is usually abbreviated with this squiggle, which is a sigma squared. And population variance is also not terribly difficult to calculate. So what the general equation for the variance is, we take the sum of our data, and I abbreviate the data with xi, minus our mean. We square that, and we divide it by the number of n, by the number of counts. So how would that look like? We have So our first data value was 10 minus 20 squared plus 20 minus 20 squared plus 30 minus 20 squared. And these 20, these are always the mean of the population. And then, of course, we divide by 3, that's the number of our observations. And let's quickly do the calculation for that. 10 minus 20 is negative 10 to the power of 2, plus 20 minus 20, that's 0 squared, plus 30 minus 20, that is 10 squared, divided by 3. It gives us minus 10 squared, that gives 100, plus 0 plus 10 squared also gives 100, divided by 3. So here we have 200 divided by 3, and the value for sigma squared for our variance therefore would be 66.67. That is our population variance. Very often people don't like variances, so what they use is they use the standard deviation. So in this case it's the population standard deviation. Standard deviation. And this is just simply the square root of our variance. So here the population standard deviation is the square root of 66.67, and when I get my calculator out I calculate this to 8.165. So this standard deviation gives us the spread of this population. So now we've characterized our population and our data. We have a mu of 20 and a spread in terms of the standard deviation of 8.165. So now what happens if we look at our data from a slightly different point of view? So we have 10, 20 and 30, and we say, okay, we've done this experiment, whatever this experiment was, we've done that 3 times and we got 3 observations. But what would happen if we actually do this experiment far more often? If we do it 10 times, 20 times, 1,000 times, 1,000,000 times, what would we get in terms of the mean? What is actually the true mean? The true mean for this experiment. For this experiment, if we do this experiment 50,000 times. Experiment. So we can use our data as a sample and say from this sample we make a prediction Oh, okay, excellent. So I've just got a comment from Joshua. Josia, I don't understand. Okay. That's great. Now I know that actually this works. So thank you very, very much for this comment. First of all, let me try to figure out what is the problem that you don't understand. What we can do is we just simply take these 3 data points and say, well, next time we might not have 10, 20, 30. We do an additional one. Let's say we do another 10, or we get 15, or we get 25, or something like that. So these are all the experiments that we potentially could do. We could do 1,000,000 experiments. And we want to know actually what is the correct mean of all these data. And for that we just simply use our 3 data to make this prediction. Does that sort of make things a little bit clearer? And I just wait here. So what we just simply do is we use our 3 data points and try to make a prediction how the mean would look like. Brilliant, thank you. How the mean would look like if we did the experiment 1,000 times, or let's say if we did the experiment an infinite number of times. Of course, we can't do the experiment an infinite number of times, but we could, well, at least to try a lot more. But then, you know, we might be a little bit lazy and not want to do that. So how can we predict? As I said, we treat our data set as a sample. And for a sample, we try to figure out the sample mean, and that's very easy. The sample mean, and usually this is abbreviated with X bar, to distinguish it from the population mean, where we said it's mu. But X bar is again calculated exactly like the population mean. We just simply add our data points, 10 plus 20 plus 30, and we divide by the number of observations. And you see the X bar is exactly the same thing as is the population mean. And we've done that, 10 plus 20 plus 30, that gives us 60, divided by 3 equals 20. So that is our sample mean. Sample mean is 20 in this case. Okay, so that's our sample mean. And we make the prediction that even if we did the experiment 1,000,000 times, the mean would be around 20, somewhere in the region of 20. It probably won't be 1,000, it probably won't be minus 500, it will be probably somewhere in the region of 20. Although we just have 3 samples, it would be very difficult to say that actually our mean, when we did the experiment 1,000 times, it will be exactly 20, but we can try to figure out, a range in which the mean of all the experiment is located. So how do we do that? Well, what we need to do is we need to calculate the standard deviation of our sample. So sample standard deviation And the equation for a sample standard deviation is fairly similar to what we have done with the population standard deviation. There is a slight change in it. So the sample standard deviation is abbreviated with an S. And what we do is we sum up our differences between the individual data point and our sample mean. This is x bar. We square that, and now we divide by, and here comes the big difference. When we said for our variance we use n, we divide by n. When we deal with a sample, we divide by n minus 1. So let's quickly do that. Let's do the calculation for that. So we have S equals the square root of, so we have 10 minus 20 squared plus 20 minus 20 squared plus 30 minus 20 squared. We had three observations, so we have 3 minus 1. And let's just simply do the calculation. S equals square root of, so we said 10 minus 20 squared, that gives us 100, plus 0 plus 100 divided by 3 minus 1, that is 2. So S equals square root of 200 divided by 2 equals square root of 100. S equals 10. So that is our standard deviation for the sample. Our sample standard deviation. And remember, when we looked at our population standard deviation, we had 8.165. So what we can say is that the sample standard deviation, and I abbreviate it as this, is always larger than the population standard deviation. And what we can do now is we can try and figure out where is our range. Where is our range for the mean? And for this, we can say it is x bar plus minus the margin of error. Margin of error. How do we get this margin of error? Well, what we need to do is, so MOE, that's our margin of error, equals T, and that is a factor I will discuss in another lecture. So that's a specific factor. Specific factor times the standard deviation that we just calculated divided by the square root of n. So we want to be fairly sure with our margin of error, so we usually call it a 95% margin of error. And in this case, our MOE equals this t factor. It depends on how sure we want to be, and on the size of our sample. Now, for n equals 3, t equals 4.303. And I show you in a different video how you can easily calculate that. So, for our MOE, we now have 4.303 times the standard deviation that we just calculated. That here is our standard deviation. 10 divided by the square root of our number of observations, so that was 3. Now let's try and do this calculation. So it is 4.303 times 10 divided by square root of 3 is 1.7 something, 1.73. And if we put this together, we get for our margin of error something along the line of 24.84. So that is our margin of error. And we said for our range in which we predict, let me write this down, prediction of the mean, prediction of mean. If we did the experiment 1,000, 10,000, million, 10 million times, the prediction of the mean would be our sample mean plus minus the margin of error. So we would have 20 plus minus 24.84. And we can calculate that. So it would be negative 4.84 to 44.84. Anywhere in between here, between negative 4.84 and 44.84, we predict that our true mean of an infinite number of experiments would be located somewhere in between here. We do not know exactly where it is, but this is a fairly good estimate of the mean. And that is really as good as it gets. So we can't get any closer. We can't say the mean will be actually between 18 and 22 or so. If we want to do that, we would have to increase for more precise prediction we need to increase the sample size. So instead of 3, if we did the experiment, let's say 300 times, then we would get a far better idea of where the true mean for all the possible experiments that we could do in this case, where this would be located. So I think I will leave it here. I just want to quickly summarize. For description of data, description and visualization, we usually treat the data as a population. For predictions, we usually treat the data as a sample. So I hope this makes sense, and if you've got any questions, please do message me or ask questions. I'm very happy to answer all your questions. So thank you very much for watching, and I hope you enjoyed that.